Hello and welcome to another live session for our MOOC. Welcoming your questions on any topic in astronomy. I'll do my best to answer.
So our first question is from Mike, who is on with us live. The question is regarding a long manned trip to Mars that we are planning. Wouldn't it be better to build a ship much like that in the movie Mission to Mars with a rotating module for simulated low gravity versus humans floating around for 6 to 9 months in 0G?
That's a good question, and the answer to your question is yes. It would clearly be better. The cost in terms of atrophy on muscles and various other bad things that happen in the optic nerve system in the brain cavity. I mean, the number of bad side effects of zero gravity witnessed by astronauts in the space station who spend that length of time in orbit is not insignificant. And of course, then these people have to function in the weaker gravity of Mars and then do it all over again to come back. So yes, a artificial gravity Mars probe with the astronauts aboard would be a better solution. Unfortunately, that's an area where The Martian, the book by Nick Ware and the movie, the same name, otherwise excellent, made a few bendings of the truth. And that mission, that hypothetical mission that you saw in that movie was punitively expensive. To build that kind of a spacecraft of that size and complexity with artificial gravity would up the cost of a minimalist Mars mission by a factor of 3 to 4, like the best estimates I've seen from engineers. So that's not going to happen because the humans to Mars mission is already costed at something like $50 to $100 billion. And upping that by a factor of 3 or 4 takes it beyond the reach of being doable. So unfortunately, the first Martian visitors are going to have to tolerate all the risks of zero gravity, of high radiation doses, and uncertain situation they will find on the surface of the planet.
All right, the next question comes from Amid. This is from a previous live session that we didn't get to the question. If a black hole pulls all light inside the event horizon, then can we see the past if we go inside a black hole?
That's a fascinating question because the theory of black holes is essentially mute on the subject of what goes on inside the event horizon. So the simple answer to the question is we don't know. All we know, the simplest way to describe an event horizon is an information membrane. And so rather than just talking about light, the more generalized way to talk about it is information that can't get out of the event horizon. It's trapped inside. So that means not just light, but all electromagnetic radiation, particles, anything that could possibly carry information. That's a sort of computer science way of thinking about black holes as sort of information sinks. So what does the theory say about inside the event horizon? The simple black hole theories, they're not that simple. They, of course, use general relativity, fiendishly complex mathematics. But the basic calculations done in the 70s, starting actually earlier in the 30s and 40s, but then in the 70s by theorists like Stephen Hawking and Jacob Bekenstein, who recently died, very famous black hole theorist, did indeed speculate about what might happen inside a black hole, whether the singularity is a true infinite point of mass and density, what happens to time-like events, or what happens to the arrow of time inside a black hole. And there are fascinating conjectures, and they're just conjectures, that in spinning black holes, and essentially all black holes will be spinning because they form from the collapse of stars that are spinning more slowly, so they will have angular momentum. In those situations, what would have been a point-like singularity is actually stretched into an annulus or a disk. Actually an annulus, or actually a ring. It essentially has no second dimension. It's a one-dimensional ring. And if you go through the theory of black holes such as it exists, then you can actually have time-like curves on that ring where you can move backwards and forwards in time. So it's not quite what you were asking in the question. It's not like the history of all the things that fell into the black hole can be spooled backwards in reverse by going inside the black hole. But there are possibly some space-time configurations within a black hole that allow you to violate the causality condition, which is forward only in time, never backward. That's fascinating. Unfortunately, because this information and these strange configurations are bounded by the event horizon, and that's an information membrane, there's no way for us on the outside to diagnose this situation or to test whether these theories are correct. The only way to do it, of course, would be to send someone into the black hole to find out. And then you'd have a logical problem because whoever you send in to find out would actually know, but they couldn't get that information back out to anyone else.
All right, the next question is from Victor via email. We know that the solar wind was responsible for the depletion of Mars' atmosphere. Does the aurora also have some effect on our earthly atmosphere?
I'll modify this fairly declarative statement of the question, which is mostly correct. We strongly suspect that the solar wind was responsible for part of the depletion of the Martian atmosphere, which in turn was responsible for Mars drying out and the water content of Mars either evaporating into space or going into frozen underground state. That solar wind, of course, does interact with the Earth. The main difference, and indeed it affects the aurora, it's part of the causal phenomena of the aurora, that energy deposited by the solar wind into high energy particles in the upper Earth's atmosphere, particularly at the polar regions, is what causes the aurora. It's this cascading effect of initially cosmic wind energy, which is both electromagnetic and high energy particles, into cascades of ionized particles flowing along magnetic field lines near the polar regions. And the ionized gas is what gives the color, and the variations of flow of plasma along the magnetic field lines is what give the shimmering sheets and striations of the beautiful aurora effect. Now, the big difference then, back to Mars, between the Earth and the Mars, is that in the mass of the planet, the Martian magnetic field is much weaker. And it's, of course, the magnetic field of the Earth, being much stronger, that both deflects, in a sense, protecting us from the solar wind, especially the adverse effects, and, of course, acts to funnel that energy into these polar regions of aligned magnetic fields, causing the aurora. So the Earth's in a doubly good situation. One, it's protected from the solar wind by the strong magnetic field present because the Earth is large enough to have a liquid molten magnetic core, and because that interaction gives us the aurora. So on Mars, you're missing both things. You have a weak magnetic field, you have total exposure to the solar wind, and you don't get an aurora.
All right, the next question is again from email, and they ask, in space there is no atmosphere, so how do spacecraft propel themselves as Newton's third law of gravity does not apply?
So Newton's third law does apply, actually, and that's the basis for understanding propulsion. It does seem intuitively strange that you can easily imagine propulsion on the Earth's surface or in a terrestrial situation where you're pushing against something. In the most obvious way, it might be a propeller or oars in water where you're pushing against the water and moving yourself forward. Or it might be a jet or a rocket exhaust on the Earth just pushing backwards against the ground or the air. So how can that work when you're in space and there's nothing to push against? And the answer is Newton's laws do apply. Space travel is fundamentally based on Newton's laws of motion and Newton's law of gravity. And for every action, an equal and opposite reaction applies, and indeed is the basis of space travel. So the best way to think of this is in terms of conservation of momentum, one of the fundamental principles of physics. And the conservation of momentum principle says that the product of mass and velocity is always conserved, or is on one side of an equation is equal to the other side of the equation. So in a rocket, the situation you have is that the rocket, which has a large mass and which you want to get to a modest, but in absolute terms fairly small velocity, is exactly balanced by the exhaust gas from the rocket engine, which constitutes a small amount of mass, but which is accelerated to a much larger velocity. So it's that equation, it's that Newton's law, which explains spaceflight. You're essentially creating a mechanism through a rocket engine to accelerate the fuel. You get energy from the fuel. Use a nozzle to create an exhaust speed that's extremely high, tens of thousands of meters per second. And that in turn gives the rocket, the larger mass, a relatively smaller forward velocity or acceleration. But that's sufficient for space travel.
The next question is from Emery. What would happen to the planets in the solar system if the sun suddenly disappeared?
Yeah, if the sun disappeared, one of the ways I've heard this question asked before is what happens if the sun turned into a black hole, which it can't do. It's not massive enough to. But if some evil genius alien empire squashed the sun down to a small city size, formally becoming a black hole, the light would disappear, and so life on Earth would eventually be extinguished, but the orbit of the Earth wouldn't change, nor any of the other planets, because black holes only distort space-time close to them. And so if you keep the mass constant, you actually don't change the Newtonian orbits. If the mass suddenly goes to zero, however, that's a completely different situation, and it's actually very easy in Newtonian mechanics or Newtonian gravity to say what will happen. Essentially, all of the planets would then just continue on a trajectory that represented a tangent to their current position in their orbit. In other words, take the position and the direction, instantaneous direction of the motion of each of the planets at the time the sun disappeared, and just draw a straight line, of course, leaving the solar system, and they would all just go out on straight line trajectories from their current positions. Because it is the sun that causes non-uniform motion. The planets are in a continual state of acceleration, where that acceleration really constitutes the change of direction that has them in an orbit, rather than any particular change in velocity. So, of course, the question is a hypothetical that could never happen because of conservation of mass, another conservation principle. You cannot just suddenly extinguish the sun. But if you could, then the planets would just fly off into interstellar space.
Okay, the next question is from Jonathan, who is on with us live. And they're interested in how much of a problem is radiation for missions to Mars?
It's a problem for sure. The issue is mass and cost. In principle, you could shield humans in a spacecraft to Mars with heavy metals, lead, but probably not lead, just other slightly lighter, dense metals, alloys essentially. You could possibly shield them, radiation shield them quite successfully, but the cost in mass, and therefore in rocket fuel, and therefore in cost in the mission, is prohibitive. So using conventional spacecraft technologies, which obviously have shielding, because the shielding for most spacecraft really revolves around protection from micrometeorites, which are a particular danger in near Earth orbit. So if you just use conventional spacecraft, like the Apollo capsules or the Soyuz capsule, something like that, then in an 8 or 9 months journey to Mars, the humans aboard would essentially have a lifetime dose, maybe a bit more, 30% more of radiation in less than a year, and then the same again on the way back. So what does that mean? 1.5 to 2 lifetime doses of radiation just for the purpose of going to Mars. It actually, by the calculations I've read, increases your cancer risk from radiation-associated cancers by 7 to 10%, some number like that. It's actually not a huge amount. So in the risk calculations of missions to Mars, that radiation dose is substantial, but it's not considered prohibitive, and the people who do it are actually going to be facing much more serious risks and threats. Now, the other factor, of course, is how long they're on the surface of Mars, because Mars not being protected from cosmic rays, and it being sort of uncertain how shielded their habitat would be. If they were on the surface of Mars for many months, then you can add another lifetime's worth dose of radiation. So the longer they're on Mars, they might start to pile up a really significant hazard of downstream cancer.
All right, Michael submitted a question through email and asks, please describe your personal observations of the recent solar eclipse, and do you have any comments about the apparently massive solar flare seen on the northern hemisphere of the sun?
Yeah, so I just get back about a week ago from Indonesia. It's a pretty nice place to have to see an eclipse. You know, various people at work raise their eyebrows because I go on a 2+ week trip to Indonesia, pretty nice part of the world, for a 2-minute event. It was really only 2 minutes of totality in that location. So I was on a tour where there were 4 astronomer lecturers and enrichment lecturers and tour guides for the eclipse. And there were 70 of us. There was so many we actually had to split into subgroups, and we all only came together for the eclipse itself. On the morning of the eclipse, or the day before the eclipse, we flew to Belitung Island, which is a small island off the coast of Borneo on the path of totality. The path of totality, of course, arced across the Pacific Ocean, and there was the longest amount of totality was in open ocean, essentially, with no significant islands or infrastructure. So the best viewing locations were as it passed through Indonesia, particularly through Borneo and Sumatra. But Borneo and Sumatra are, you know, tropical islands with large amounts of moisture. Basically, the weather there at this time of the year, most of the year round, is like 85 degrees and 85% humidity. So the odds of being clouded out or were very high on Sumatra or Borneo. So the person who organized this trip chose a place called Belitung Island, which is a small island between, essentially on a map, between Borneo and Sumatra. Because it's a smaller island with less vegetation, the a priori odds of being clear for the eclipse were about 70%. It was touch and go. We were there. The eclipse happened at 7:21. Totality was 7:21 local time in the morning. And we were woken up at 4 a.m. to drive 2.5 hours to the north part of the island where we had a clear view to the rising sun. And there were multi-layered clouds around that time. So, you know, there were enough hardcore astronomers on this trip and people with pretty serious camera gear that they were going to be very unhappy if they'd done this whole trip and traveled all that way for nothing. It more or less cleared for totality, and then the exit phase was mostly clear. Entry, first contact to second contact, was mostly cloudy. So people got what they wanted, and it was very spectacular. Actually, having little clouds scattered around the sky almost makes the effect more dramatic when the eclipse occurs. Many locals were there. There were thousands of locals, very few Westerners, in fact. And it was a pretty good eclipse. As for the solar activity that was witnessed, one person in our group actually was using a coronagraphic technique and actually got a picture of the prominences in the corona. We didn't see it till days later. In fact, it took a while for him to do some processing on his images. So we saw that it's slightly anomalous behavior for the sun, but not out of the realm of things that happen every few years on the sun's surface. Otherwise, you know, Baily's beads were hard to see for this eclipse from this location. So I would say, according to people who've seen dozens of eclipses, I've only seen 5, this was in the middle tier of eclipses.
All right, the next question is from Janet via email. An article published recently talked about a scientist working on what time really is. Specifically, subatomic particles called K and B mesons were found to behave slightly differently depending on the direction of time. Basically, do you have any comment on this or discuss what these findings mean?
Yeah, there's the history of this is that there are strong conservation principles in physics, in fundamental physics, that are really foundational in terms of how we think physics works. Some of these principles are conservation of energy, conservation, which is more properly discussed as conservation of mass energy, hyphenated, because the two can be interconverted. And then there are conservation of momentum, conservation of angular momentum. These are physical principles where in any interaction or change of situation, these physical quantities are conserved in the sense of an equation, that the entity, whether it's mass energy or momentum or angular momentum, cannot be created or destroyed. Another very profound, maybe even more profound symmetry principle in physics is called PCT conservation. So in a system of any interaction involving subatomic particles, any subatomic particles, it was observed starting 50 or 60 years ago that the product of parity, which is the orientation of the spin of a particle, subatomic particles all have some parity, some spin. They can be spin zero, but generally they do have spin. Charge, which is electric charge, positive or negative, and the time arrow, whether the interaction moves forward or backwards, is always conserved. And that's a very powerful principle in physics that was observed to generally hold, with the level we could determine it. Foundational principle, in fact. The effect that you're talking about with these mesons was actually starting 40 or so years ago. There were subtle interactions involving the creation and destruction and interactions of these K-mesons where charge, the product of charge and parity, was not conserved. There was a very slight violation in the before and the after situation involving these mesons. And if the overriding conservation principle is that the product or the combination of charge, parity, and time must be conserved, and they observed that the product of charge and parity was not conserved in these interactions, then the inference was that time conservation is not absolute. This effect was very small. It's a subtle, maybe a few % effect in these interactions. But that sort of essentially opened the door to the idea of the non-conservation of the arrow of time, meaning that there's some foundational way in which physics is not completely time symmetric. Remember that up until that point, it was just a true principle of physics that subatomic particle interactions could, under appropriate conditions, flow backward or forward in time, and no one had seen any instance where this didn't happen. With this discovery, with the mesons of CP violation, as it was called, the inference is that time conservation is not absolute. And so physicists have been looking through the decades for instances where fundamental interactions do not flow equally in forward and backward time, and they found some instances of this. Now, what this means for physics, does this mean that there is possible to create time travel or violate causality on a larger scale than individual subatomic reactions? Nobody knows. But it's a fascinating feature of fundamental physics, and since it doesn't have a natural explanation in the standard model of particle physics, it's yet another indication, if we need it anymore, that standard subatomic physics is not a complete theory yet.
The next question is via email from Sunil, who asks, in space there are asteroids, but there are other even smaller objects moving at very high speeds. During, say, a trip to Mars, could the spacecraft be hit by these smaller objects? If so, how dangerous are they? And what precautions can be taken in the design of spacecraft?
Yeah, I mean, it's a real concern. The practical answer is that the risks, the risks, as in total failure of the spacecraft, are actually small, but they're not zero. I think, when we're just factoring all the risks of a Mars trip involving humans, that's in the mix, but it's a lower probability of failure than, the rocket engine failing or the entry stage of the rocket going wrong or the landing stage having a problem and the astronauts die from impact. These are all considered much larger risks. The astronauts will travel, or visitors to Mars will travel in the ecliptic, that is the plane of the solar system, and on all the debris, not just asteroids, but comets that are in the inner solar system and just space junk, debris, rocky material of all different sizes, is mostly distributed in the plane of the solar system, which means if you're since you're not going to hop out of the plane of the solar system and then back in when you get to Mars, energy cost of that is enormous. You're in the regime where you're going to be traveling where all the debris lies. But the main thing to remember is that, yes, there's debris there, but the debris particles are still very small. They're rarely more than 1 meter across. And they're pretty rare. They're very sparse, and space is big. So when people go through the calculation and calculate the probability that something pea-sized, I mean, all it takes is actually something much less than pea-sized. Grain of sand, if it's traveling at 10 kilometers per second, could rupture the shell of a spacecraft. But even so, the odds of that impact happening in an 8 or 9 month journey turn out to be very small. How small? Seems to be less than 1%. But it's a random effect, and the point and the problem is that you have no warning. There's no way to track these particles, since such a small particle can cause devastation to a spacecraft. We have no catalog of them. We have no advanced warning system. We have no way of deflecting them, even if we could see them heading for a spacecraft. So this is simply a risk that the astronauts will have to accept.
Right, the next question, again, is from email. And this one gets slightly political, but in a funny way. Is it true that the non-use of the metric system messed up the Mars Climate Orbiter in 1999? If so, or if I remember correctly, it cost the US well over $150 million. How is it possible that the US scientific community, at the very least, doesn't insist the US pass on to the metric system, as you are the last country on Earth still using British Imperial measures?
Yes, that's a great question. It's a pet peeve of a lot of scientists, of course. This fact that we haven't officially adopted metric. So to the immediate question, yes, absolutely. NASA did their big mea culpa. It was at the engineering phase, the early design phase of that spacecraft. You think it would be done by computers and cross-checked, even if it was in a spreadsheet that someone built by hand. In the interconversion from English to metric units, there was a conversion error, and that led to the spec on, not just one, actually a number of critical components being wrong, and that in the end led to the failure of the spacecraft. So this $150 million loss is assigned essentially entirely to this metric conversion error. In a sense, you could say it was a management failure, that you didn't have enough project oversight or double checking or cross checking to catch it. It's something that you would imagine should be caught. But clearly, it's a problem that's going to happen as long as you have two systems of units in play. So I would say the main answer to the main context, which is absolutely Thomas Jefferson argued, one of the founding fathers, was a keen observer of the political scene in France, and he noticed the good and the bad things that happened in the French Revolution. One of the things he was aware of was how the French adopted this highly rational, and essentially invented the metric system. The kilogram and the meter, if they are no longer physical objects, they're defined in terms of pure physics now, but as they were physical objects, they've existed in Paris at the International Institute of Measurement. And so France bequeathed the world the metric system, a great gift to the world, and America spurned it. Thomas Jefferson, back in his day, was so confident that the young nation of America would adopt the metric system that he didn't really even push for it very hard. It was so self-evident to him, as in the other self-evident truths of the New Republic, that he just thought it would happen. And as he got older and reached the end of his life in retirement, he was incredibly dismayed that there was resistance. Now, what he would have thought, that another 2 centuries had passed and you still have milk sold in gallons and gas sold in gallons. There's imperial gallons and non-imperial gallons, and that we're still using non-metric system. It totally annoyed him, there's no doubt. However, the scientific and educational communities and the technical communities in industry and in academia essentially use metric system for everything they do. So what's happened is that the professional world of scientists and engineers has essentially just voted with their feet and done what the rest of the world is doing, which is use metric. And that's what you'll see in international conferences, that's what you'll see in papers, that's what you'll see in software that scientists and engineers use. And so, scientists and engineers just live in a world where in their everyday life they have to encounter gallons and pints and inch and feet, and then in their professional lives they are pretty much fully metric. So it's not a terrible situation. You can sort of get over that dichotomy, I suppose. But it is a shame that the country as a whole has not seen fit to move to the metric system. Because, as many people point out, not even the English use English units anymore.
All right, the next question is from Gerald, who is on with us live. In the proton-proton chain in fusion in a star, there's a release of a positron, which reacts with an electron with the release of energy in the electromagnetic spectrum. Is that release or created energy a gamma ray? If so, do we know what the amount is?
Yes, definitely. So that's right. There's a 3-step process in the proton-proton chain, and then the first step, positron is released in the transmutation from neutron to proton, and that's conserving charge, of course. And that, because antimatter in a fundamentally matter-rich situation will not travel very far at all before it encounters the particle and annihilates. The energy released when an electron annihilates with its counterpart is 500 and 511, I think, MeV, million electron volts. And if you convert that into radiation energy, it is indeed in hard gamma ray region. So each of these proton-proton chain interactions releases a strong, sort of very high energy gamma ray. And at each stage of the chain, you're releasing gamma rays. So this is what the energy source in the center of the sun is. Now, by a process of diffusion, radiative diffusion, these photons migrate their way out through the star until they're released from what we see as the photosphere. And that diffusion path takes tens of thousands of years, by which time they have degraded in energy to become yellow visible photons with an equivalent temperature of 5,700 Kelvin. So the sunlight we see is the sort of diffusive relic of all these gamma ray photons that were produced by annihilations in the center of the sun.
All right, the next question comes from Mark via email. What are the benefits and dangers of using nuclear-fueled rockets in manned space exploration?
Well, the benefit is that we move to the next stage of the space game. Essentially, everything done in space travel, even by innovators like Elon Musk and Jeff Bezos, is done with chemical fuel. They're using essentially, very volatile versions of kerosene, and that releases about as much chemical energy as you can get from a molecular interaction. But it's essentially factors of hundreds of thousands, actually to millions, up to 10 million times less energy per interaction than you would get from a nuclear fusion reaction, or indeed a fission reaction. So going to the nuclear fuel involves a fantastic gain in efficiency of the fuel, how much energy you get out per mass of the fuel you use. So the motivation for doing it is enormous. I mean, it would completely remove the obstacle that we have currently, which is we're never going to get beyond the solar system with these kind of fuels, these chemical energy fuels, which is just rearranging electrons in an atom. So that's the benefit. The benefit is a fantastic gain in efficiency and the possibility of opening up space travel beyond the solar system. The downside, or the hurdle, if you like, is technological. The technological hurdle is that when you're talking about fusion, which is the clean and easy way of doing this using the abundant fuel of hydrogen, the most common element in the universe, we have not, despite 50 years of effort and hundreds of billions of dollars of research dollars, we have not yet managed to have a self-sustaining fusion reaction on the Earth. And if we get close to it, it's essentially for a nanosecond at a time using gear that weighs 1,000 tons. That's pretty far from being sort of nimble like a spacecraft. So, we are so at an early stage in our harnessing of fusion power that we can't even project when we might get this kind of a capability. So the interim step is to consider, a slightly more clunky way of doing this than a completely self-contained fusion reactor. And that's essentially to use the more uncontrolled version of this, which is to create small nuclear explosions. The Project Daedalus, which dates back from the 1960s in Britain, and other designs from the 60s and 70s, have imagined how we might use many small nuclear detonations essentially released behind a spacecraft, and then you have a big reaction plate, which is just essentially a large amount of metal mass spread out that will take the impulse from that nuclear explosion to give a slight shove to the spacecraft. So the model here is of creating thousands, probably tens of thousands of small nuclear detonations behind the spacecraft to just sequentially push it forward and accelerate it. So that is a technology we can do because we do know how to make nuclear bombs, which are essentially uncontrolled nuclear reactions. And these would be just very many small versions of these explosions. So that's probably the only thing that's even within, I would say, decades or maybe half a century of being able to be developed. And there are some visionaries and some research entities, groups, and think tanks that are trying to push forward towards that goal. NASA's reanimated what was called its 100-year Starship program that operates out of NASA Ames in the Bay Area. That was a visionary idea of taking some of these propulsion concepts and developing them. And it sort of went dark, if you like, for a decade or more. They've reanimated that, and there is interest in the engineering community on how this might work. But these are very challenging technologies, and I would say in terms of NASA's plans or the major space powers plans, they're decades away.
All right, the next question is from email as well. Is there any experimental evidence of other dimensions of space-time, or is it only theoretical? Are these only theoretical predictions of string theory at this time?
They are just theoretical predictions at this time. I mean, I can summarize briefly because there's not much observational approach to this subject. It's very difficult, what we do and we don't know. In string theories, as the question implies, posit extra dimensions of space-time that are in most of the theories compactified or accessible only on extremely small physical scales and correspondingly high energies far beyond anything obtainable in accelerators. So that's part of the answer. We cannot test these theories, these string theories involving multiple dimensions, with the current generation of accelerators. Remember, these are huge machines that cost tens of billions of dollars, so it's going to be hard to do much better than current accelerators like the Large Hadron Collider. So what have people done? Well, they've actually, some of the theories, which are, it's interesting, we're not talking about one theory anyway, we're talking about a suite of theories, a little bit unbounded by observation, of course. Some of the theories of extra dimensions predict that there might be manifestations of these hidden dimensions on what are called essentially macroscopic scales of a meter, which corresponds to lab physics. And so there are some tests being done at places like Livermore, Los Alamos, various physics labs around the country and the world, trying to look for hints of extra dimensions in terrestrial scale physics in the lab. They're testing particular variations of string theory, not the whole gamut of string theories. Every now and then there's a new result or publication in this area, and so far there are null results. There's no evidence of such effects. People are continuing to look. So I would say this is an area of somewhat frustration because the theorists are still quite enamored of string theory. They think it solves some very fundamental problems in physics. The experimentalists are frustrated because all of the predictions involve situations, almost all the predictions involve situations that we just cannot create on the labs of the Earth. So these theories remain, for the most part, untested and perhaps untestable even in principle.
The next question comes from Kathleen, also via email. What do you know about the 2 comets in the news this week, and where do you think comets come from?
So on the first, I'll have to beg ignorance. I've having been away for 2.5 weeks with the eclipse, I'm way behind on my news cycle. I'm still trying to catch up with the politics and everything else. And so on my science news, I'm behind. So I don't know, I can't talk about those comets that you're referring to. The origin of comets, though, is pretty well understood. In the 1950s, the repository of comets, these periodic visitors to the inner solar system in the vicinity of the sun, was hypothesized by the Dutch astronomer Jan Oort to be a large quasi-spherical cloud existing enormous distances from the Earth, a good fraction of the distance to the nearest stars, which is to say potentially 50 to 100,000 astronomical units, where Earth-Sun distance is 1 AU, and the full extent of the planets of the solar system is 40 AU, so huge distances. By Kepler's laws, these comets on highly elliptical orbits would spend most of their time, 99.9999% of their time, very far from the sun, extremely distant, and so essentially unobservably faint, and of course not lit up, no tails, no halos, because they're so far from the sun's radiation. And then we only see them when they come into the inner part of the solar system, when they either get big enough and bright enough by reflected light to detect them with a telescope, or the sun activates them and then they shine in the sky and they're really obvious. So the Oort cloud, as it was called, was a hypothesis from the 1950s, and it was really hard to test because the bulk of these comets, for most of their time, are sitting at this enormous distance of close to 1 trillion miles away. And in fact, the Oort cloud hypothesis has not been completely tested beyond doubt. But what's happened in the meantime with larger telescopes is we've been able to track comets much further in their orbits to where they are really heading well beyond the solar system toward the Oort cloud. We've also measured enough comets to get a sense that they are in a pretty much spherical distribution around the Earth. They don't just inhabit the ecliptic, the plane of the solar system. And so, you know, with a high degree of probability, the Oort cloud hypothesis is correct. The inventory of comets is also poorly constrained by observation for the same reasons, but it's of order 1 trillion. So we're essentially talking about about 1 trillion small rocky and icy objects, where small means a few kilometers up to maybe 10 or 20 kilometers, living at distances of hundreds of billions or about 1 trillion miles from the Earth.
All right, this question is via email. It's kind of an old email, but the question is, the rivalry between Isaac Newton and Robert Hooke is well known. Do you know of any more recent examples of professional rivalry between astronomers that deteriorated into similar animosity?
Yeah, I mean, it would be hard to match the animosity of the Newton-Hooke rivalry. And actually, the Newton-Hooke is only one version of the rivalry that Newton had with other fellow scientists. Newton was famous for not getting on well with his colleagues. The Hooke rivalry was particularly intense because Hooke was a brilliant scientist in his own right, made important contributions to optics, to astronomy, to the theory of how mechanical objects behave, mechanics essentially. So his work overlapped with a lot of the kind of things that Newton was doing, including theories of color and so on. And Newton was relentless in trying to put his ideas on top of Hooke's, and as was famously noted in several of his biographies, when Hooke died, he continued to keep criticizing him and trashing his reputation, and he even, in the face of Hooke's widow's strong protestations, he even used his position as the president of the Royal Society of London to prevent Hooke's papers from being published posthumously. I mean, that's pretty vindictive. So Newton and Hooke, you know, really had an ugly rivalry. Newton, of course, also famously warred with Leibniz over the invention of the calculus, and so he had a series of rivalries. Does anything in the modern era match this? Not really, nothing quite as epic, and of course nothing, it would have to involve a very famous, extremely famous scientist. There have been some pretty intense rivalries that have got to the level perhaps of animosity, but I think generally they're a little more good-natured. I mean, in science, obviously there was an intense rivalry associated with the discovery of DNA, so not in astronomy anymore, but in the discovery of DNA. And even then in the parsing of the human genome much more recently. In astronomy, there was an intense rivalry over the discovery of dark energy by the acceleration of supernovae, involving two rival research teams. There were a couple of people who were on both teams, but those teams were kind of at each other's throats for a few years until they realized that they were actually making their results stronger by checking and testing each other. So the dark energy accelerating universe result is a slightly more recent example. But I can't think of anything that really rivals the animus that Newton had for some of his colleagues.
All right, the next question comes from Cecil, who was on with us live. Is there a particular achievement in your work that you would hope to accomplish before you pass?
Wow, that's a depressing thought. So my research has shrunk, my astronomical research has shrunk to the border a day a week, and there's no limit to what I can accomplish there with a small amount of support. I mean, my financial support is now devoted mostly to education and MOOCs and educational technology. And so on the science side, I would say working with one graduate student that I have still doing this kind of work, understanding the mechanism by which the black holes in the center of galaxies are inactive for 99% of their time and active for 1% of their time? That's a big open question in observational cosmology, if you like, and how galaxies work. As opposed to quasars or active galaxies being special objects, they're just like normal galaxies, like our galaxy, all of which have supermassive black holes. And for some reason, most of the time, most supermassive black holes are inactive, even though there's plenty of gas and stars at the center of a galaxy. So that's been a puzzle for a while now, and I doubt I can be the one to solve that solo, because it's teams of people that work on these problems. So that's the one thing that is still an enigma in my field, extragalactic astronomy, that I would hope to make an impact on.
Right, the next question is from Mohammed, who's on with us live, and the question is, can you please explain the holographic principle? Are you familiar with that, and can you explain it?
The holographic principle is sort of taking black hole theory to the next stage beyond the early to mid 70s work of Stephen Hawking, which defined the basic properties of black holes and their interiors. The holographic principle is a speculation. I mean, it stems from Hawking's work and Bekenstein's work, the famous person I alluded to a while ago who died just in the last year. And actually Bekenstein was one of the authors of the holographic principle. The holographic principle is the idea that even though the event horizon of a black hole is an information membrane, that we cannot, whatever flows into a black hole, matter or energy, is lost to us forever. The holographic principle states that in some way the properties of what falls into a black hole are embedded or are coded in the event horizon itself. And so if we could somehow read, like a hologram, as information is embedded in a hologram, and if we could only figure out some way to read the hologram, doing the reverse experiment as you do with holography, when you create a hologram, that we could get out the information of what went into the black hole. Now, why did what was motivating the holographic principle? Was this what's called the information paradox, the fact that the black hole, as we understand it simply, is mute to whatever went into it. In other words, if you make a black hole by throwing lots of subatomic particles into a small region of space until it's a black hole, or by colliding planets in a small region of space until they become a black hole, or throwing a bunch of old random socks that people have lost in their drawers and cupboards into a black hole, the black hole all look the same. They all have the same mass and the same properties. And so somehow the black hole is losing that. It's in loss of information of what went into the black hole. And that has been called the information paradox. It also has been called the entropy paradox, or the entropy problem of black holes, because black holes embody an enormous amount of entropy. Entropy is the number of equivalent microscopic states. And essentially, since we can't distinguish between all the multitudinous ways a black hole could be created from different pathways, the black hole embodies a huge amount of entropy in the universe. A black hole, the mass of the sun, has 100 million times the entropy of the actual sun. And that's also part of the motivation to the holographic principle. So the holographic principle is a proposal, speculation, that information is not lost, and that the black hole entropy is not perhaps as large as we might naively calculate, and that somehow that information is embedded in the event horizon. Now, Stephen Hawking, in a sort of lyrical way, has said we shouldn't imagine the information coded like a barcode or a QR code that we can just scan with a wand and read. He imagined, his analogy was that if the information in a black hole represents an encyclopedia, then what we might access on the event horizon represents the scattered ashes of the encyclopedia after it was burned, and we might discern some information. That's Hawking's version of the pathetic amount of information that might be available to us, holographically preserved. But it's still just a supposition. Nobody has deduced, nobody has hypothesized a way of inspecting the event horizon to somehow extract that information. It's still a viable theory, though, and most black hole theorists seem to subscribe to the holographic principle.
Right, Gerald, who's on with us live, would like to know if you have any opinion on the existence of the Hydrino as espoused by Randell Mills.
So I'm going to claim ignorance on this one. I don't know what the Hydrino is. It's a subatomic particle, obviously, but I'm going to have to pass on this one.
We'll have a problem. The next one is, the next question is from Danny via email, and this is, his specific question is, can we avoid adding habitable moons to the Drake equation much longer? But I know that you've talked about that in the class, so could could you expand on that and just discuss where are we in the state of what we think the the current solution to the Drake equation would be, and the number of possible.
The problem with the Drake equation, as alluded to in the question, is that habitability is defined in a fairly conventional way. It's conventional in two senses. First of all, habitability is defined in that traditional way where it's a planet at the suitable range of distances from a star where the surface temperature is somewhere between the freezing point and the boiling point of water. That's the simple definition of habitable zone. So that's naive in a very obvious way, because as soon as a planet has an atmosphere, and if it's going to be a habitable living planet, it will have an atmosphere. That atmosphere has a greenhouse effect, and as with the Earth is about 20 degrees Celsius warmer than it would be at this position if it had no atmosphere. If it has more greenhouse gases, then it's warmer still. So the habitable zone already has to be modified by the presence of an atmosphere, but we don't know the atmospheres of almost any of the exoplanets found so far. So we just have to set that aside. The second problem with the habitable zone argument is that it's very centered on the surface properties of a planet. And we know that life exists under the oceans of the Earth. It exists in deep rock, immune from solar radiation. So there's life in environments where solar radiation is not providing the energy for that biology. So right away, that says that the habitable zone, is not a formally complete concept, because you can have biology without being in that habitable zone. And that's for a terrestrial type planet. And then the third issue alluded to in the question is that we now know of a handful, and possibly as many as 10 or 12 moons of giant planets in the solar system, or habitable spots, ranging down to tiny Enceladus, a very small moon of Saturn, where there are all the ingredients for microbial life. And there you're very far from the habitable zone. You're in what's called the cryogenic biosphere. So the simple answer to the question is yes, astrobiologists have started to loosen the bounds of the Drake equation, because they've had to admit that in the solar system, the cryogenic biosphere has, of order 10 times as many spots for life as the one spot for life where we know it exists, the Earth. And some papers have already started to incorporate the cryogenic biosphere into their definition of habitability, which means they've explicitly tried to include the likelihood of habitable moons as well as habitable planets. So yes, people have modified the Drake equation in this way. The problem, of course, is that while we've had great success in finding potentially habitable planets with Kepler, we have not found a single exomoon yet. There's some controversial claims and some claims that might actually be confirmed within the next year or so. But basically, in a situation with 5,000 exoplanets, we have 0 exomoons. It is just too hard at the moment to detect exomoons, let alone to decide whether they're habitable. So embellishing the Drake equation in that way is not necessarily useful, because we've just added an ingredient that we have no observational data on.
Right, so there is a potential astronomy student who has a question about what are the best universities in the world to study astronomy, or the best affordable universities to study astronomy?
So that's a good question. It's a big question. There are, and I do know enough of the universities beyond the US, I can answer it in a question of the world situation. But basically, you're also talking about affordability. So if you're talking about private universities, some of the best programs are indeed private universities. In the US, among the top 10 programs are Harvard, Caltech, Chicago, MIT, and Princeton. Those are all private universities with high sticker prices, but for well-qualified students, they tend to provide very strong scholarship and fellowship support. And so many science students and many astronomy students at those private universities get a full ride, or they're essentially having almost all their tuition and fees and maybe even some living expenses covered. So you shouldn't rule out the private universities just because on the face of it they're less affordable. for good students, they're often quite affordable. Of the public universities in the U.S., we are among the top 5 public university astronomy departments. That's the University of Arizona. And I would say the others would be University of California, Berkeley, University of California, Santa Cruz, University of Texas at Austin, University of Washington, University of Michigan. Then there's a number of others, actually. That's a kind of a variable cohort. Colorado also has a strong astronomy department. So there's probably a dozen or 15 programs that are very strong, where grad students from those programs go on to get good employment. Outside the U.S., it's a larger landscape, of course, and I'm not as fully aware of it. Within the UK, place I am familiar with, so if you're speaking English, it's an easy place to go and work. The strongest programs are probably the strongest of all is at the University of Cambridge, and then the next strongest programs might be Imperial College, University of Edinburgh, Manchester, all the major universities in the UK for other subjects as well. And then around continental Europe, it again tends to be the major universities. Australia has very strong astronomy programs at Mount Stromlo in particular, at the University of Sydney. And in Canada, similarly, there are strong programs at the major universities, McGill, University of British Columbia, and Dominion Astrophysical Observatory, which is associated with an astronomy department. So there's a lot of astronomy programs. There are probably 25 to 30 in what I would call the top tier worldwide. They're very selective. For graduate programs, they will tend to admit 5 to 10 students out of 100 to 150 applicants. Those are our kind of statistics. But if you're well qualified and have a physics and math and astronomy background, then you're going to be competitive.
All right, and we have several other questions, but we are out of time, so we will pick those up next week from our email. And thanks everyone for joining us.
Thanks for joining us. We're going to get a slightly more rapid pace since I've been away for a few weeks, so we will be having a live session next week and a few weeks after that. So thank you for asking your questions today, and I'll talk to you again soon. Bye.